So today's video we'll be looking at the steady state heat of conduction through a composite wall. So now when you say a composite wall, it means that you are referring to different slabs of walls that have been combined together. Right? So we have different walls made up of different materials, and then we are combining them together to make it a composite shape. So we are calling it a composite wall. So this is our wall A, our wall B, and then our wall C. So now what you should understand first is that when you have any heat transfer, right, passing through the wall, the heat transfer that passes through the wall one, let's say wall A through to wall C, you see the same heat transfer. So if you are calling this kill inlet, then kill outlet, then we see that kill in will be equal to kill out, right? So at each point, so now from this outer surface to this inner surface here, the heat transfer through from here to here will be the same heat transfer from here to here, and to be the same heat transfer from here to here. And that's why the heat transfer in will be the same as heat transfer going out. Right? So now if each wall has a thickness, so let's call the thickness XA, XB, and then XC. Because of course the thickness can't be the same. In some cases the thickness might be the same, but the worst case scenario you can get is that the thickness are not the same. So we are going to use that to derive what we want. And then each wall has its own thermal conductivity. So Ka, Kb, and then Kc. Right. So now, when the temperatures of the walls are different, so let's say it starts from here, right? Because there is heat transfer. So here has a temperature of, let's say, T1. And then at this thickness, that temperature of T2. And here temperature of T3. And here is T4. Right? So if I'm enlarging it, we have T1, T2, T3, and then the last one is T4. Yes, so because this T1 will have a higher temperature than T2, and T2 have a higher temperature than T3, T2 have a higher temperature than T4, there will be heat transfer, right? So now what I'm saying is that the heat transfer from this point to this point will be the same as from this point to this point, the same as from this point to this point. Now when you are taking each layer, each wall are standing on its own. Because the heat transfer is by conduction, they are walls by conduction. We are going to say that our heat Q1, so we are calling Q1 to be the first one, right? Okay, let's say QA because the walls are A, B, and C. So the heat transfer through the wall A will be K of A multiplying our area A, right? Multiplying our T. So now our T, we are going to use change in temperature. So T1 minus T2 because we are seeing T1 is at a higher temperature than T2 all over our thickness XE. Right. So now we are assuming that the area of the walls are the same. Right. We are saying that the thickness are not the same, but the areas are the same. Why? Because we are seeing it's a composite wall. Right. So the same length and then the same breadth. We can't actually see the breadth because here we are taking this part to be our thickness. So it depends on the view we are looking at. But then so far as they have the same top and then the same down and then they have the same length. So we are assuming that they have the same breadth also. So in this case, they have the same length and then the same breadth, but the thickness are not the same. So area A, and then when you're talking of QB, the heat transfer through wall B is going to be our KB, our A, the same area. So T2 minus T3 all over XB. We are using KB because they are made up of different materials, even though the areas are the same. Right? So the area can be the same, but the materials are different. And then the thermal conductivity depends on the material used. And our QC now becomes KCA multiplying T3 minus T4 all over Xc. Now this is the heat transfer through wall A, heat transfer through wall B, and heat transfer through wall C. Now we are saying that the heat transfer at each wall will be the same, right? Now from our previous video, we were able to establish something which was called the thermal resistance. So the whole idea of thermal resistance is that it's going to help us to know how much heat is being prevented from entering the wall. So if you have a heat entering, right, we can have our Q. We said our Q is equal to Ka change in T over the thickness. And we were able to establish that if this is our current I and this is our voltage V, now the rest becomes our resistance R, T8. So for conduction, our RTH was change in X over Ka, right? So we can establish that here and say that R of A will now be XA over Ka times area. R of B will now be XB over KB times area. And then R of C will now be XC over KC times area. Yes. So now from the heat equation, we can see that if this is our RTH, then we can say that heat is now equal to change in temperature all over our resistance, right? Because our resistance now is change in X over Ka. So when we put that here, we're going to get change in X all over Ka, and then it comes to. So it means that we can write our rate of heat transfer to always be temperature difference all over thermal resistance. So all over resistance, right? So we can write this as a heat transfer equation henceforth. So this is what we're using henceforth. We don't need to write everything again. And then we know that if you are dealing with conduction, our RTH is X, change in X over Ke, and then we can calculate for the RTH separately, and then we come and divide by the temperature difference and get our heat. So that's what we are doing here. So now we can also see that our Ka will now be T1 minus T2 all over our Re here, right? Because we are saying our K is equal to temperature difference by the resistance. So if this is our temperature difference, then our resistance will be R, right? So all over Re. Then our QB will also now be T, because our QB is this, T2 minus T3 all over RB, right? And then our QC will now be, this is our QC, T3 minus T4 all over RC, right? Yes. Now we know that QA is equal to QB is equal to QC. If we establish this, and then we can see that this is equal to Q. So let's just call it heat transfer. So the heat transfer throughout the entire walls, right? From here to here is the same as from here to here, the same as from here to here, the same as from here to here, the same as the one leaving, the same as the one entering. Right? So we are calling them Q. So Q will now be T1. Sorry, so Q will now be T1 minus T2 all over RA. For the B part, Q is equal to T2 minus T3. I'm referring from this. All over RB. And then the same Q will now be T3 minus T4 all over RC. Right? So we can get something here and see that T1 minus T2 will be equal to QRE. Right? And then we can see that T2 minus T3 from this equation is equal to QRB. And then T3 minus T4 is equal to QRC. RC. So this, let's call this equation 1, equation 2, and then equation 3. So now let's try and add equation 1, 2, and 3. So when we are adding them, we are going to get T1 minus T2 plus T2 minus T3 plus T3 minus T4. So someone will ask, why are we adding? So we are adding to get the overall heat transfer, even though they are the same. True, they are the same through each wall and even at the end and at the start. We are adding them to get the overall temperature difference, right? So if this at temperature of T1, let's say 100 degrees Celsius, and this at let's say 80, this at 60, and this at 30. So we want to find what's the overall heat transfer or the overall temperature difference from this point to this point. And that should be equal to QRE plus QRB plus QRC. You realize that this and this will cancel out, this and this will cancel out. We are left with T1 minus T4. And that's actually what I was talking about. So T1 and then T4 should be equal to, we can factorize our Q out, and then we are going to get RE plus RB plus RC. So our Q now becomes T1 minus T4 all over RE plus RB plus RC. Right. So now we can establish something here. We can establish something here and say that our Q is equal to temperature difference, which is T1 minus T4 all over RA plus RB plus RC. And then we can see that our Q is equal to our change in temperature overall, right? Our overall change in temperature, because from this, our overall change in temperature will be from T1 and then T4, and that's what we have here. So T1, overall change in temperature all over summation of all our thermal resistances. But you realize that we ended up getting RE plus RB plus RC, and that is going to give us change in T overall all over. So from this are our XA over KA times A plus XB over KB times A plus XC over KC times A. So this are overall or summation of all our thermal resistances, and then this are Q, and our change in temperature overall becomes the very highest one, which is at this point, and then the least one at this point. So this becomes our quantity of heat. So now when you have any question and then it's about composite walls, because this scale is the same as this scale here, and the same as this, and the same as this. Anytime you are being asked to find the heat transfer through the wall, you can use any of the equations. So if you have your T1 and your T2, and you have your RA, you can find it using this. If you have your T2 and your T3, and you have your RB, you can find it using this. So any of them would work. So what we establish now is that when you want to find the heat transfer, it's change in temperature overall all over summation of the thermal resistances.